So hi everyone. In this video we're going to be finishing the last part of section 11.3 in the textbook called Estimate of Sums. Now I'm going to give you a heads up, this is a little confusing, but hopefully throughout this video it'll become clearer. So in the first part of the 11.3 video we learned about the integral test, which told us whether a series converges or diverges if the improper integral converged or diverged. But now we're trying to answer a different question. So sometimes a series does converge, but we don't know its exact sum. So what do we do then? So we add the first several terms, use that as an approximation, then estimate how far off we are. So basically, that's what this video is about. So the general idea is, if you use a partial sum to estimate the full infinite sum, how much error do I make? So now let's go on to the main concept. So let's suppose, so I'm going to write this down. So suppose we have a convergent series So here, S is the actual full sum of the infinite series, and suppose we only add the first n terms. So this gives us a partial sum, so S of n is equal to however many terms we decide to add. That is our partial sum. So just for clarification, S is the exact full sum, and S of n is the approximation using the first n terms, which could be however many terms. So since S of n is only part of the series, it's usually not equal to the actual sum of the series S. So we define the error, or also you can call that the remainder, by R sub n, which is equal to S minus S sub n. So the actual sum minus the partial sum, which should make sense logically. So R sub n is going to tell us how far off our approximation is from the actual sum. So if we estimate R sub n, or the remainder, then we know how accurate our partial sum is. So that's the main concept. So now we're going to be moving on to a notation that we're going to be needing. So first off, we have the exact sum. Now if you don't want to write this down, that's fine, because it's going to be there later in the video. The exact sum is going to be we saw this earlier. Then we have partial sum, which is going to be however many terms you want. Lastly, we have error of remainder, which is going to be your actual sum minus your partial sum. So this is the amount that we are missing after stopping on the nth term for this. So now let's go on to the theorem. So it's basically the same as the integral test. So here's it. If the series comes from a function f of x that is continuous, I'm just going to write continuous as the short way, positive and decreasing, then the error satisfies. So this formula is kind of long. So integral from infinity, or from n plus 1 to infinity of f of x dx just less than or equal to the remainder, which is greater or less than or equal to remainder, and the remainder is less than or equal to from n to infinity of f of x dx. So this is called the remainder estimate for the integral test. Now, you don't have to memorize all this, but just basically note that the true error is trapped between the two improper integrals. So that's basically the key idea, because I promise you, if I try explaining all this, it would be really confusing. And if we want the bounds for the exact sum s, we add the partial sum to everything, so it'll look like this. I'm going to write it in blue. So if you want bounds, I'm going to write, if we want the bounds for the exact sum s, we add partial sum to everything. So this is what it looks like. So it's going to be s sub n plus, and that just the whole integral we wrote on the top, from infinity to n plus 1. So this gives us a lower bound and an upper bound for the true sum. Now, I know this is really confusing right now, like the formula and everything, but this is basically saying that if you stop after n terms, then you are missing the rest of the series, right? So that missing part is the error. And the theorem says that we can estimate the missing part using integrals. So we will explore this concept later, and hopefully I'll try to clear it up so this makes sense. And don't worry if you didn't write the formula down. There will be an end slide with all the formulas and everything you need. So when do you use this? So you use this when, first of all, the series is positive and the function is continuous, positive, and decreasing. You note that series converges, and lastly, you want to know how accurate a partial sum is. So this is not where you're going to decide whether a series converge or diverge. This is where you say that you know your series is converging, so how close is your approximation? So you can write this down really quick. Now we're going to go over the step by step. So here's your step by step how to estimate a sum. So step 1, you want to find the partial sum. Step 2, you want to write the error. Step 3, you want to use the equation for the remainder estimates. I'm going to write it down again. And then slash, I'll just write evaluate these. So step 4, if you want bounds, so if you want the bounds, for the exact sum S, you add the partial sum, or Sn, to all parts. And then for the last step, this is really conditional, it depends. So if the problem asks how many terms are needed, solve the upper bound inequality. So we will see step 5 an example and also the rest. So this is a step-by-step method for now. So you can write it down if you want to, and now let's actually move on to example. First problem, use a partial sum, or S sub 4, so in this case the fourth partial sum, to estimate the sum of 1 over n squared. So our step 1 is to find the first 4 terms. So we need to add them. So how are we going to do that? So let's write S sub 4. Now we need to find the first 4 terms. So let's start. So we know S4 is equal to, it's going to equal to the first term plus the second term plus the third term plus the fourth term. So let's look at our first term. So our first term, you just plug in a 1, right? So what is 1 divided by 1 squared? Well, 1 squared is just 1, and 1 over 1 is just 1. Let's look at our second term. What is 1 over 2 squared? Well, we know 2 squared is 4, so that's just 1/4. Now for a third term, what is 1 over 3 squared? We know 3 squared is 9, so we know the third term is 1/9. Lastly, we have the fourth term. So what is 1 over 4 squared? Well, we know 4 squared is 16, so it's just 1/16. So now we're going to add all 4 of these terms. So side here, let's write sub 4 is equal to 1 plus 1/4 plus 1/9 plus 1/16. Now we go to add all these. So I already added these up. If you want, you can find a common denominator for each of them and add them up, or for this case, where it'll be easier if you use a decimal, and in most cases you'll use a decimal because the fractions are going to come out to like something like absurd. So for this one, it's like 205 over 144. So in most cases you'll have a calculator and you will be able to, or the numbers aren't going to be this extreme, like a fraction. But for this case I already calculated it, so the decimal, so we have S sub 4 is approximately 1.4236. So now that we have that, we are going to write out our error estimate. So I'm going to move this aside and erase. So we're going to move this to the top corner, and I'm going to erase the rest. Okay, so now we're going to write the error estimate. So we know our function is just 1 over x squared. If you remember from the last video, you just replace the n's with x's. So plugging this into the remainder estimate formula, we get the integral from 5 to infinity. Now why is it 5 and not 4? But if you remember, in the formula, the left side was n plus 1. So we're writing a fourth partial sum, so 4 plus 1 is 5. So from 5 to infinity of 1 over x squared dx is less than or equal to fourth remainder of, which is less than or equal to, 4 to infinity of 1 over x squared dx. So now, all we gotta do is just compute the integrals now. So let's start with the lower bound integral, so this one. So we write on the side, infinity of 5 of 1 over x squared dx. So this is also the same thing as rewriting this as x and negative 2 dx. When you take the integral, oh sorry, actually we got to rewrite this, the limit notation, since it's improper. So the limit is b approaching infinity of b to 5 x and negative 2 dx. Now we can take the integral. We know the integral of that, so you just add 1 divided by 1, so negative 2 plus 1 is just negative 1. Divide by that is just, so it's just going to be negative x to the negative 1, or you can just rewrite this as negative 1 over x. Therefore, we're going to have limit b approaching infinity of negative 1 over x from b to 5. Now all we gotta do is plug this in. So we're gonna get the limit is b approaching infinity of negative 1 over b minus negative 1 over 5. So we're going to distribute the negatives here, so this negative will cancel out. And since this term is going to be positive, I'm going to move this to the front so it looks cleaner. So this is going to be equal to the limit b approaching infinity of 1/5 minus 1 over b. And now we can plug in. So we know that whenever you put an infinity into the b, 1 over infinity is just 0, so 1/5 minus 0, you're just going to get 1/5. Therefore, we know the lower bound is 1/5. So I'm going to write it down here next to the S4. So we have our lower bound is equal to 1/5. So I'm going to erase this, but if you're confused with the math, if you're confused where I got the 1/5 from, I'll do it really quick on the side. So if after we distribute the negative to the parentheses right, it would be like this. Limit b approaching infinity of negative 1 over b plus 1/5. I just moved that plus here, so it could just be a minus. That makes sense. So it's just 1/5 minus 1 over b. That's all I did. This makes it, I guess, tiny bit neater, but you don't really gotta do it. So yeah. So now we're gonna go ahead and look at the lower bound, or compute the lower bound. Sorry, upper bound. What am I saying? So the upper bound is same thing, from infinity to 4, 1 over x squared dx. As you know, since they're the same integral, so you don't really gotta do anything. So we know this is just gonna be x to negative 2. Can we write this as a limit notation? You know, this just gives us negative 1 over x. Now we just plug that in. Sorry if my B's look a little weird. I kind of suck at using my Apple Pencil. So just distribute that and get. So remember, negative, distribute the negative, we get positive 1/4. So we'll move the 1/4 in the front again. You don't have to. Minus 1 over b. Now you know when you plug in the b, infinity for b, that's minus 1/4 minus 1 over infinity, which is basically 0. is equal to 1/4. So we know the upper bound now, you probably would have known that the upper bound is 1/4 since you know it's the exact same thing as the top integral we just took, but instead of a 5, it's a 4. So if you could tell by looking at it, that's good, but I would still just do the integral just in case if it's a test or something like a homework, just in case the teacher wants to see work, so never skip that. Now, let's rewrite this error bound. So that's our, I guess, step 5. So write the error bound. So we just computed this, right? What did we get? For the lower bound, we got 1/5. This is less than or equal to the fourth remainder, which is less than or equal to the upper bound, we got 1/4. So this big, giant, messy integral just becomes this simple. So if you know 1/5 is 0.2 and 1/4 is 0.25, so that means that the actual error is somewhere between 0.2 and 0.25. So now we got to turn this bound into the actual sum. So if you remember the formula we had, the fourth remainder is equal to the actual sum minus the partial sum. So it would look like this. So it's going to be 1/5 less than or equal to s minus s sub 4 is less than or equal to 1/4. Now if you're wondering why this is the middle, if you can see, R4 is equal to that, right? So we just replace this R4 right here with the S minus S4. So what do we do? Well, if you didn't know from inequality, if you add something, so let's add the partial sum of the fourth partial sum to both sides. If you add something in between an inequality, you have to add it to both sides. So that's where you get the actual sum bound error formula for. The one before, hold up, where was it? Go back to it really quick. This one right here in blue, that's where you got the SN, the partial sum stuff plus, because you just replaced that. But I just wrote that down without you guys knowing that it's just a simple, like it made sense because you're just replacing the R4 with the definition, or the fourth remainder with just the actual sum minus partial sum. So that's where that formula comes from. It's literally just adding the partial sum to both sides. So hopefully that gets rid of some confusion. So it's going to be, you're going to get fourth partial sum plus 1/5, which is less than or equal to s, and which is less than or equal to fourth partial sum plus 1/4. And earlier in the video, we did find, that's the first thing we did, right? We found the fourth partial sum right here. To the rather top right, it's 1.4236. So all you got to do is just add these two. So it's going to be 1.4236 plus, remember 1/5 is just 0.2, plus 0.2 is less than or equal to s, or the actual sum which is less than or equal to 1.4236 plus 0.25. And when you put this in your calculator, you get 1.6236 less than or equal to s, so less than or equal to 1.6736. 67. Sorry, I'm not funny, I know. So your exact sum is between 1.6236 and 1.6736. 67 again. So using your fourth partial sum, we estimate that is going to be your estimate. That's the interval where the true sum lies, even though we actually don't know the exact one, but we just found the interval. So hopefully this became a little bit clearer. So I know the formulas kind of look intimidating, intriguing, but you're just basically plugging in two integrals, and they're all the same function, right? So once you solve the first integral, they're all the same function. You can just do that for the second one, and you find your numbers, just plug it in, and life's good. So it's pretty simple to do. Now, example 2. This is a different problem. Same function, but different problem. How many terms of the sum of 1 over n squared do we need to make the error less than 0.001? So what we want to know is that we want the error to be less than 0.001. So we want, whoops, remember the error and remainder, same thing. So we want the remainder or the error to be less than 0.001. So if you remember in the theorem right here, step 5, if the problem asks how many terms are needed, solve the upper bound inequality. Therefore, the theorem, we know that r sub n less than equal to integral from infinity to n of 1 over x squared dx. Now, if you don't remember what the upper bound one is, so this is the lower bound right here. Here I'll write in blue. This was the lower bound. This, sorry, I should do that in a different color. This was the upper bound. So that's why it's n. So now we just solve. So this is just saying that the integral infinity to n 1 over x squared so we compute the integral. So let's do this on the side really quick. From infinity to n 1 over x squared versus just x to negative 2. So we got to rewrite this in the limit notation since it's improper. So we did this integral like what, 2 times already? So I know this is just going to be equal to the limit. It's b approaching infinity. This is just negative 1 over x from b to n. So now it's negative 1 over b minus negative 1 over n. Again, distribute the parentheses. This becomes a positive 1 over n. I'm going to move this to the front like I always do. To the limit. It's b approaching infinity of 1 over n minus 1 over b. You plug in infinity for b, you know that just goes to 0. So it's going to be equal to 1 over n. So the upper bound is now, it's going to be r sub n, or the error is just equal to 1 over n. Now we can just replace that with the 0.001, so it's going to be 1 over n less than 0.001. So 0.001 is also can also be rewritten as 1 over 1,000. So cross multiply, you got to flip the sign, so it's going to be n is greater than 1,000, right? So that means that the first whole number that works, because remember its n is greater than 1,000, not greater than or equal to, because look at the theorem right here. I'll highlight in blue. It's the error is less than 0.001, not less than or equal to. So it's not equal to 1,000. So the next whole number that comes up is, well, what comes after the whole number after 1,000? 1,001. That is your answer. So we need at least 1,001 terms to guarantee that the error is less than 0.001. That's a lot of terms if you ask me. But yeah, that's basically it. Now you don't have to solve it the way I did for this. You can obviously multiply by n or like flip the fractions, do whatever. Well, I guess I basically flipped it too because you have to flip the sign, but yeah. So that's how you calculate a term where it asks you for how many terms you need when the error to make this error less than a certain number. So here's the recap. So here are the formulas, just in case you didn't write it down before. You have your exact sum, partial sum, you got your error, remainder estimate, bounds for exact sum, and then you already know when to use it. You use it when a series is positive and decreasing, and you want to estimate the sum of the error. So this concludes the section of 11.3 and tells us that how to estimate the sum once we know the series converges. So thank you for watching, and if you have any questions, again, leave in the comments. Thank you.